Hi, everybody. This is Dr. Nigro with a chem calculations screencast that's also going to serve as a little firm up for some information that we talked about in class this week covering selective precipitation. So I just wanted to take a few minutes to clear up what I feel was some confusion around the calculations for this particular chemical technique and just make sure that we're all on the same page. All right. So again, as a definition, we know that selective precipitation is a lab technique where we are targeting the precipitation of one ion over another in a mixture of ions. Now, we can be targeting a cation over other cations or an anion over anions. But the key is that we are going to exploit differences in the solubility of these ions to extract one ion over another. All right, so what does this really look like? So I have a beaker, all right? That beaker contains multiple anions. We've got chloride, iodide, and bromide, all right? So if we're going to add in silver, we know based on the solubility rules that we get insoluble compounds between silver and the halides. So we're going to get multiple different precipitates if we add in this silver. All right, so multiple precipitates from a single solution. All right, so if we're going to look at this example specifically, one thing we really need to know is what are the KSP values for these different solids. So our options here are going to be AgCl, AgBr, and AgI. All right, so silver halide basically. So our KSP values for silver chloride is 1.8 times 10 to the negative 10th. For silver bromide, it is 7.7 times 10 to the negative 13th. And then for silver iodide, 1.5 times 10 to the negative 16th. Now, I just happened to write these from the top of the table to the bottom, and I don't know if you noticed, but you see that the solubility is decreasing as we increase the size of that halogen. All right, but that is a discussion for a different screencast. All right, but in general, we've got our smallest value here, and we're going to go down to the largest value. So remember, right, all of these compounds have the same number of ions, all right? And if we assume that we have the same concentration of each of these ions, then we can utilize the difference in the KSP values to determine which solid will precipitate first based on that KSP value, all right? So remember, the smaller the KSP value, the less soluble that particular ionic compound is, all right? So in this case, if we look clearly, the silver iodide's KSP is the smallest of these three. All right, so that means that once we start adding in that silver ion, as we increase the concentration of the silver ion in that solution, we're going to reach a point where we've got enough present that the silver iodide precipitate is going to begin to form. And we're going to see the formation of this ionic compound first, all right? Once we reach that level, we may not have enough yet for these two solids to form, the silver bromide and silver chloride, all right? So they do not form at the same point. So they do not form at the same concentration of, not iodide, sorry, silver ions, all right? They're going to have their own value, all right? So how do we know what that is? Well, all right, if we look down at the beaker below, here we've got I'm actually going to slide this down a little bit. Come on. All right, we've got a different beaker. For this one, I've got potassium iodide and I've got potassium chloride in there, and I've got concentrations of those two compounds, 0.001 for the potassium iodide and 0.1 for the potassium chloride. And I'm going to add in some silver nitrate. Well, I can use my KSP values to determine how much silver ion I'm going to need to precipitate out this particular amount of the iodide and the chloride. Now, that is something I think was less clear when we talked about it in class, right? We do not have any solid in solution initially, all right? So we're not really using an ice chart for these calculations. What we're doing is looking at that KSP value. If we know the concentration of one of the two ions, we're finding the other. So it's closer to the problems we worked earlier in equilibrium, where we had all of the equilibrium concentrations but one, and then we knew the K value. So we used that K value and those equilibrium concentrations to calculate the missing concentration value. That is what these problems more closely resemble. All right, so let's start with our potassium chloride solution. All right, so we're going to be forming a silver chloride. So we're going to have a KSP value that's going to be equal to the concentration of silver ions and the concentration of chloride ions. All right, we plug in our KSP value, 1.8 times 10 to the negative 10th. And our unknown here is going to be the silver. All right, we know that in solution we have 0.01 molar of our chloride. I know that because potassium chloride is a 1-to-1, right? One molecule of potassium chloride contains one ion of chloride. All right, so then we're going to do the division and we're going to end up with X, and in this case X is equal to the concentration of Ag plus, which is going to be 1.8 times 10 to the negative 9th molar. And if we have that much silver in solution, we will get precipitation. All right, so you can see there's no rice chart here. There is just solving for this unknown quantity at equilibrium. All right, now we can repeat this, but we're going to look at it from silver iodide's perspective. All right, so this time the silver ion concentration times the iodide concentration. All right, we know that the KSP value for silver iodide is 1.5 times 10 to the negative 13th. Or, oh, nope, sorry, 1.5 times 10 to the negative 16th. Excuse me. All right, so we'll have an X for the silver amount. According to the beaker, we have 0.001 molar Ki, which means we have 0.001 molar I minus. So we'll put that in for the I minus amount. And then again, we're going to solve for X, which is going to be equal to the silver concentration under these conditions. And we find that this is 1.5 times 10 to the negative 13th molar. All right, and so that is the amount of silver that needs to be free in solution. And once we go over that amount, we are going to see precipitation. All right, so this is our precipitation level. All right, so you can see that clearly, even though we have way less iodide present, we still need less silver to start that precipitation. Now, if we knock that amount, I don't know, down to 1 times 10 to the negative 9th iodide, then we might be able to see the chloride precipitate first. But you really would have to manipulate those amounts. All right. So what are we really expected to be able to do with this? Now, when you get to college and you take a general chemistry class or organic chemistry, you're going to get to actually do these selective precipitations in the lab. And that's where it's the most powerful, when you can actually see that by adjusting your concentration values or selecting particular solutions, you can pull out these individual ions. All right, but for us, the questions we really want to know is just generally, which ion will precipitate first? All right, and that's just in general, without knowing anything about what we're putting into solution or our molarities, just based on their KSP values, which of these is going to precipitate first? All right, now remember, you can utilize the comparison of those KSP values, but only if you have the same number of ions in your two comparative ionic compounds. If you don't, just take that KSP value and calculate the molar solubility of each, and then use that molar solubility for your comparison. All right, so which ion will precipitate first, second? All right, with concentration values, which precipitates first? All right, and so that's closer to that problem we worked right above. All right, if you know the amounts of some things that are present, you can utilize that to decide if something's going to precipitate in front of something else. All right, and then finally, what solutions will allow for separation. All right, and what I mean by that is if all you're given is a mixture of anions or a mixture of cations, and you're asked to choose a solution that can lead to selective precipitation, it's really the understanding of the solubility rules and an understanding of what the KSP values are for the potential precipitates that might be there. All right, so that's more of a qualitative look. The first two are more of quantitative, and that third one is qualitative. All right, so what I want to do is a couple problems, and then I'll end with a little bit more explanation just to make sure that we all kind of understand. A beaker, it contains 250 milliliters of a mixture that is labeled as 0.1 molar strontium nitrate and 0.0005 molar lead nitrate. A person slowly adds solid sodium carbonate to the beaker until a precipitate starts to form. All right, so first, given these conditions, what substance starts to precipitate first? All right, so that's our first question. And then second, what is the concentration of carbonate when the first precipitate starts to form? Okay, so let's start by thinking briefly about what is going on in terms of the particles that are present. All right, so let's say we have a beaker, and in this beaker, we have some strontium nitrate. All right, so that means that is soluble, so we're going to see some strontium, and we're going to see some nitrate ions in here. All right, and then in addition, we have some lead nitrate, so that means there'll be lead ions floating around in here as well. All right, now, when it comes to the addition, all right, we are going to be putting in, let me move this over a little bit. We're going to be putting in some sodium carbonate. All right, so that means that we're going to see carbonate floating around in there and along with our sodium. Now, I'm just going to take a moment to remove my spectator ions, right? Because nitrate is not going to impact anything. It's not going to interact with any of these ions that are present and form a precipitate. All right, and by the same token, neither is sodium. All right, so our spectator ions are our sodium ions and our nitrate ions. So they're irrelevant to the overall process here. But that carbonate is important. All right, so if we think about it, we're going to get two potential precipitates. All right, so the precipitates that are possible here are going to be lead 2 carbonate, so PbCO3, and strontium carbonate, SrCO3. So those are our two potential precipitates, and the table up here lists those KSP values. So for lead 2 carbonate, it's 7.4 times 10 to the negative 14th. All right, and then for our strontium carbonate, it's 9.3 times 10 to the negative 10th. All right, now if I look, these two ionic compounds have the same number of ions, so I can compare these two KSP values directly, and my prediction is that I'm going to see the lead carbonate precipitate first based on that KSP value, which means that the strontium carbonate should precipitate second. All right, now that's just in general. I have to prove it. All right, so that's where looking for what the minimum amount of carbonate is going to come in to this question. All right, so I need to look at how much lead and how much strontium I have in solution and what that means in terms of the amount of carbonate that I need to cause this precipitation to happen. All right, so to ID, the first precipitate, I need to calculate the concentration of carbonate that I need for each solid formation. With the given amount of cation. All right, so I'm going to start with strontium carbonate. I'll just do it SrCO3. All right, now The KSP is going to be equal to the concentration of strontium ions times the concentration of carbonate ions. All right, now we could write out our dissociation reaction here, and it's 1-to-1. All right, so I know that I don't have any squares or cubes or any of that stuff. All right, so I'm going to plug in my KSP value, so 9.3 times 10 to the negative 10th. All right, and I'm going to go back to the problem and I'm going to see, well, how much strontium is here? So I have 0.1 molar strontium nitrate. All right, so for every mole of strontium nitrate, I have 1 mole of strontium. So that means if I have 0.1 molar strontium nitrate, then I have 0.1 molar strontium ions. And then I put an X in for that carbonate. All right, I'm going to solve for X. And I find that the concentration of carbonate that I'm going to need with this amount of strontium for precipitation to happen is 9.3 times 10 to the negative 9th molar. All right, now I'm going to repeat this calculation, but this time with lead 2 carbonate. So there's my solid. All right, I'm going to write my KSP expression for this solid. So that's going to be lead ions and carbonate ions. All right, my KSP value is 7.4 times 10 to the negative 14th times 10 to the negative 14th. All right, I go back up to look at my lead solution. All right, now I have a lot less lead. All right, so if I think about it, for every 1 mole of lead nitrate, I have 1 mole of lead ions. So if I have 0.00050 molar lead nitrate, that means I have 0.00050 molar lead. All right, and then my unknown carbonate amount. All right, so that means that the amount of carbonate necessary to precipitate with this amount of lead is going to be equal to 1.5 times 10 to the negative 10th molar. All right, so now I'm going to compare these two numbers, right? And I'm going to see that the amount of carbonate needed to precipitate out the lead carbonate is less. All right, so I will see precipitation of that lead carbonate first. All right, so this requires less carbonate ions. So PbCO3 solid will precipitate first. All right, so if you're asked to find what will precipitate first and given amounts of the ions, you need to plug them in to your KSP expression to determine how much of that counter ion, whether it's an anion or cation, depending on what you're dealing with, and that's how you determine what's going to precipitate first. Okay? All right, so we're going to try one more. All right, this one's a little bit different. All right, for this one, all right, we've got barium sulfate, and that for barium selenate is shown here. All right, we're going to have a 0.1 molar solution of barium chloride that's added slowly to a to a solution that is 0.1 times 10 to the negative 4th molar in sodium sulfate and 0.1 times 10 to the negative 4th in sodium selenate. All right. So we have two questions. Well, I guess we're going to have to answer one before we can do the other. All right. What is the approximate percentage of the first anion that has precipitated at the point which the second anion just begins to precipitate? All right. So that's a little bit different. All right. But let's talk about what's going on first. All right. So pictures like this. All right. In which I have sulfate ions and selenate ions. All right, now in addition, I have sodium, all right, but one of my spectator ions here is going to be sodium. So I'm not going to put it in my beaker. It's there, but it's not going to participate in our reactions. So I just don't want it to clutter up my beaker. All right, so to this, I'm going to add in a solution of barium chloride. All right, now similar to my sodium, that chloride ion is going to be a spectator ion, so I'm not going to put it in either. All right, but I am going to have barium ions in here. All right, now those barium ions will interact with selenate and sulfate and form insoluble precipitates. All right, so our two precipitate options here are going to be barium sulfate and barium selenate. Okay, now if we look at our KSP values for barium sulfate, we've got 1.1 times 10 to the negative 10th. And then for barium selenate, 2.8 times 10 to the negative 11th. Now those values are pretty close, all right? For each of these, I have where is it? Sorry. Whoops, come here. 1.0 times 10 to the negative 4th molar of the sulfate. And I have 1.0 times 10 to the negative 4th molar selenate. All right, so each of these salts has the same number of ions, and I have the same concentration of each of these anions. So that means that I can directly compare these KSP values and decide which is going to precipitate first. Now, because the KSP of BaSO4 is greater than the KSP of barium selenate, this is going to precipitate first, and this one will precipitate second. All right, now, if I had different ions or the amounts of those ions were not the same, I would need to calculate, just like we did in the problem above. All right, so we know what solid is going to precipitate first. All right, I could do the math and show you that, but we can do it directly by comparison for this particular setup. All right, so now what we're asked is how much, in terms of percent, of the first anion to precipitate, which will be the selenate, remains when the second anion, which is sulfate, starts to precipitate. All right, so to answer this question, what we really need to know, well, how much barium needs to be around for that second precipitation to start? All right, because when that second precipitation starts, that amount of barium must be in the beaker. And if I know how much barium is there, I can figure out how much selenate must also be there at the same time using those KSP values. All right, we know that barium sulfate precipitates at a particular concentration. All right, so let's see what that value is first. All right, so we're going to take the KSP of barium sulfate, so barium and sulfate. All right, that KSP value is 1.1 times 10 to the negative 10th. All right, and that's going to be equal to the amount of barium, which we do not know, times the amount of sulfate that's present. All right, well, we already said we have 1.0 times 10 to the negative 4th molar of that sulfate anion. All right, so we can solve that for the concentration of barium. All right, and we find that we're going to need 1.1 times 10 to the negative 6th molar barium ions for precipitation of barium sulfate to start. All right, so once we reach this point, the question is how much of the selenate remains, all right? Because remember, what we're doing is adding in this barium chloride slowly. So the concentration of barium is building up over time, all right? Initially, we'll reach the point where the selenate has the right amount of barium for precipitation, but then we're going to eventually go past that value, all right? Because the amount of selenate is going to decrease while the barium is continually added, and eventually it gets built up to this 1.1 times 10 to the negative 6 molar level, and then the barium sulfate can start to precipitate, all right? So what we're going to do now is say, all right, well, I know that the KSP for barium selenate is equal to the concentration of barium and selenate, all right? If that KSP value is 2.8 times 10 to the negative 11th, and we have 1.1 times 10 to the negative 6 molar barium present, how much selenate must also be there at this point for the barium. All right, so X in this case is going to be equal to the amount of the anion, selenate, all right, and we find that we're going to have 2.5 or 2.6 times 10 to the negative fifth molar present at the same time that we have 1.1 times 10 to the negative sixth. All right. Now, the problem didn't just want to know the concentration, it wanted to know the percentage. All right. So basically, the percent that remains, all right, is going to be equal to this value, 2.6 times 10 to the negative fifth molar, divided by our initial amount, which is 1.0 times 10 to the negative fourth molar. And then we're going to multiply that by 100%. All right. And we find that 25% of our original amount is still present for that selenate ion. All right. But this particularly asks the approximate percentage that has precipitated. All right. So that means we need to subtract that from 100. All right. So if 25% remains, then 75% has, precipitated. All right, so again, this problem is different because it's asking us to think about what's left for the first precipitate in terms of ions once we reach the point of precipitation for the second. All right. Doing these problems where you're continually adding in one of the ions that you're using for selective precipitation, all right, that ion will react with the lower or less soluble ion first, but eventually the amount of that ion is going to decrease to the point where it's going to have a very hard time colliding and finding those counter ions. So the ion we're adding in is going to build up in terms of amount and will reach the minimum requirement for our second precipitation to occur. All right, so when you're thinking about these problems, you really need to read them very carefully. All right, if it's asking about what precipitates first, think about whether the ions match in terms of number, and then if their molarity values are the same. If they are, then you can use your KSP values to going on. All right. If they are not, if there's any sort of difference, then you are absolutely going to need to calculate the concentration of that added ion needed for each one to precipitate and compare from there. All right. Again, no rice charts needed for these. These are literally problems where you know one of the two ion amounts and you're calculating what the other one should be at equilibrium. Okay. If you have any questions, please let me know. I know that this topic is a little confusing and I'm happy to help you. All right, but you need to come see me if you need some help. Okay? All right, talk to you later.